Welcome to UVU CS3060 Lecture 8.5, where I demonstrate how to calculate the banker's algorithm. So to start with the banker's algorithm, we always have our resource instances. Now, our resource instances are used to verify how the maximums that the processes can ever request, as well as help us calculate the available resources at a particular time. Once we have the resource instances, we can go ahead and let the processes begin requesting their process maximums. Now, these process maximums are the limits to the number of resources that can be allocated, and they'll be used to calculate how many resources a process needs at a given time. We have 5 processes for our demonstration here, so we should be able to, and we have the 3 resources, and if you go through each one of these 3 resources, you'll see that they are all, each request is less than the resource instances, but totaled, they easily exceed the resource instances. Which means a process at a given time, if it requests its maximums, should be able to fit within these particular instances. But it can't. But all the processes cannot request their maximums at the same time. Now we have our process allocations. At a particular time, each process has a certain number of allocations that it has made. All these allocations should be less than the process maximums. So we can see here process 0 has 3, 0, and 2 of A, B, and C, which is less than the 6, 2, and 3. Summed all together, these should be less than the resource instances, which we will calculate in a few moments here. Now that we have the process maximums and the process allocations at time 0, we can calculate the process needs. If we take process 0 again, we can see that its maximum is 6, 2, and 3. If it has currently allocated 3, 0, and 2, that's 3 less than 6, 0 less than 2, and then 2 less than 3, which gives us a process need of 3, 2, and 1. It's just a simple subtraction from process maximums of process allocations to give us the process needs. This should be calculated before we go into the algorithm. The process needs are very important for finding a process that can run to completion. Now we can go ahead and calculate the total available resources at time 0. If we add these columns together, such as resource A, 3, 1, and 1, that comes out to a total of 5. Then we have 9 for B and 8 for C. This number must be less than resource instances. If this is not less than resource instances, we have a problem. Now once we know the total allocation of the system, we can also calculate the total available, which is just simply total allocation subtracted from the resource instances. In our case, our total available is 2 of A, 2 of B, and 1 of C. Now, this number is going to be very important to us as we move ahead. What we will do with that number is we will copy these values to a vector called work. Work is going to change over time. We don't want to really mess with this if we don't have to. And so we'll copy these values over into work and use these values to help us accomplish what we're trying to do. Part of the first step of the algorithm also is to create what is called the finish vector. This finish vector identifies whether a process has been finished logically according to our algorithm. Right now, all 5 processes are running, and what we're going to do is we're going to go through and mark processes as true, as finished, if it can acquire all the resources that it needs to finish. So for example, we know that process 0 needs 3 of A, 2 of B, and 1 of C. If process 0 can get these resources right now, then we would mark this job can finish to true. But this is where the work array comes. Notice that we have 2, 2, and 1. Clearly there's not enough of A for process 0 to finish. So we will not mark process 0 as true in the initial steps here. In any case, for step 1, we create the work vector, we create the finish vector. Now step 2, we go through and we compare our work vector with each of the process needs and see, are the needs less than the work vector? If so, we're going to add that value to a list. Now initially we're just going to add one process. There's a couple of ways this can be done. So we're going to step through this list. Clearly process 0, as we discovered earlier, cannot be run to completion because its needs cannot be met. But process 1 can have its needs met. Process 2 can't have its needs met because resource B here cannot be met. Process 3 can be run to completion. And then process 4 definitely cannot be run. It needs all 3 resources that cannot be met by work. So we choose from process 1 or process 3. Let's go ahead and choose process 1. So we add process 1 to our process complete list. Now we go ahead and perform our calculation. For step 3, what we do is first we set job can finish to true. We've chosen a job that can run to completion. And then we take these allocations, these 0, 3, and 2, and we add those allocations back to the previous work. The work plus the current process allocations gives us our new work value, 2, 5, and 3. So we've gone through steps 2 and 3. Now we need to evaluate. Can we have all the jobs finished? If they have not finished, we go back up to step 2. So we've taken process 1 out of the list. Are there any processes that can have its needs met using this work? Yes, actually. We can see now process 2 can have its needs met, as well as process 3. So let's go ahead and choose process 2. Again, we're doing this one at a time. Let's set it to true because it can finish, it can run to completion with the resources that are in work. And then add process 2's current allocations to the work vector. So that would take the 2, 5, 3 value, add 1, 4, and 1, process 2's current allocations, and give us 3, 9, and 4. And that establishes our new work vector. And we will cross that off the list. Now, can any jobs or any processes have their needs met with this set of work? And we can see that process 0 can, and process 3 can. Now, instead of just simply doing one process at a time, clearly both of these can have their needs met. We've watched 3 throughout this entire time. We're going to work with both of these processes and perform step 3 with both processes at the same time. So we go ahead and set both processes to true. Now mind you, this is different than what I've been doing. I haven't been doing multiple processes at the same time. This algorithm can be done either way. Clearly it's more efficient to just simply do both processes. And I take the resources for both processes and add them to work. So we see process 0 brings us to 696, and process 3 brings us to 6, 11, and 7. Cross those off the list, and now process 4 can have all its needs met. So we go ahead and add its resources 1, 0, and 2 to what the previous work was, and we come up with a value of 7, 11, and 9. This new work should match our resource instance, because now all of our jobs can be shown that they can finish. If you can show all the jobs can be finished, all of these values are true, then the system is safe. The system is unsafe if not all the values are true, but in the search stage, you cannot find a process that can have its needs met. So let's try an allocation. So what we're going to do is we're going to see if process 0 can make a request of 1, 1, and 0. Now, the first step in this is to check to see if it exceeds its needs. If it exceeds its needs, then it's trying to ask for more resources than it declared in its maximum. Well, in this case, 1, 1, and 0 clearly matches or is less than 3, 2, and 1. So we go ahead and continue with our algorithm. This is a test that needs to happen before you continue. So what we do is we take all of the previous allocations and we change our vectors and our arrays to match that allocation as if it happens. We're pretending here. We're not actually granting the allocation. We're just simply setting up our process allocations, our process needs, and recalculating our total allocation and work as if we were performing this allocation for real. Now, you'll see that we've added 1, 1 to A and B, which brings us up to total available of 1 and 1 and 1, and work is matching total available. So we're ready. Step 1 is complete. Now we go into our loop. Now, can any processes have their particular needs met? As we can see here, there's only one process that has 1 of A that it needs and 1 of B that it needs. So clearly process 1 works here. So we take the process allocations for process 1 and add them back to work. So 1 and 1 and 1 plus 0, 3, and 2 gives us 1, 4, and 3. And we update our work to represent this new value and set process 1 to true. Now we can cross that one off the list. Okay, now we have 1, 4, and 3 for our work, but if we take a look, every process needs more than 1 of resource A, and only 1 of resource A is available. So if none of these processes will be able to run to completion, they cannot finish, because if they try to request their process maximums, it will enter a deadlock state. If all 4 of these attempt to allocate their resources, the maximum resources, this system will go into deadlock. Now, the system is not currently in deadlock. There are still these resources available, but the system is considered unsafe because we cannot meet the needs of all the unfinished jobs. So this allocation should not be immediately granted. Fortunately, if process 0 is requesting these particular resources, all we have to do is block process 0 from actually allocating these and let the other processes continue, because we know process 1 will eventually finish and restore all of its allocations back to work, and then other processes will also finish in a particular order. The system cannot be put into an unsafe state, even though it is not a deadlock state. Again, all that needs to happen with process 0 is cause it to wait until the resources that it's requesting, this 1, 1, and 0, can be granted and the system can remain safe. So let's try another allocation. Let's give process 4 0, 1, and 1. Should we grant this? So first thing we check, does 0, 1, and 1 fit within process 4's needs? Certainly. It still needs 3, 5, and 5, which means, yeah, we'll probably, this request could be granted right now if whether or not the system is safe. We need to check now if the system is safe. So we update all of our process allocation and needs along with our vectors. So we add 0, 1, and 1, which gives us total allocation of 5, 10, and 9, and a total available of 2, 1, and 0, and move that value over to work. Okay, can any processes have their needs met? Yes, we see that process 1 and process 3 can have their needs met. Process 3 just barely having its needs met, 2, 1, and 0. So we're going to use the multiple process method and just simply take all the allocations for both of those processes and add them back to work, setting the finish flag to true for those particular processes. So at this point, we add 2, 2, 1, 0, the allocations of process 1, 0, 3, and 2 to get 2, 4, 2, and then to 2, 4, 2, we add 0, 2, and 1, giving us a final work of 2, 6, 3. Now, can any processes have their needs met with that particular work? Yes, we see process 2 can have its needs met. So we go ahead and add process 2 to the list. It's the only one that can have its needs met, so we can't use we can't just simply add multiple processes here. Once we've identified the process that can have its needs met, we set it to finish, set its finished flag to true, and then we go ahead and take these resource allocations and add them to the work, bringing us to 3, 10, and 4. So can any processes have their needs met at this point? Yes. Process 0 and process 4 both can have their needs met. So we can use the allocations from both of those processes and add them to our work vector. And it eventually comes out to 7, 11, and 9. All our jobs can finish successfully. That means this particular allocation will keep the system in a safe state. So the operating system, or the algorithm I should say, can grant process 4 its allocation request without stopping process 4. This brings us to the end of lecture 8.5, where I demonstrate the banker's algorithm.